Hey everybody, what we're going to discuss in this video is a technique that we're going to use a lot as we're using steam tables, and that's interpolation. So I just want to make sure that we're all on the same page and you're all going to get a lot of practice, but hopefully this video gives a little context to what exactly interpolation is, and I guess some way to think about it beyond the equation, which you can find posted on Moodle from Felder, which maybe you remember using before. So, all right, so here's a little snippet of a property table. This is actually one for nitrogen, superheated nitrogen. That means nitrogen gas. And say we're asked some question like this. Determine the specific volume of nitrogen at 100 kilopascal and 400 Kelvin. So we're going to go to our table. Hey, look, we found 100 kilopascal, and we're going to look and try to find 480 Kelvin because that's our temperature. And look, we have 450 and 500, but no 480. So what do? Well, we have numbers, right? This is our specific volume column. So we have numbers for specific volume at 450 and 500, but not 480. So we're going to pick out these numbers there. We'll just write it there. So I'll make a little table down here. So at 450, so we can use black because it's maybe easier to see. So at 450K, right, our specific volume is 1.33607. At 480, it's currently an unknown. And at 500, our specific volume is 1.48458. So what we're going to do basically is do a linear interpolation. So if you think about what we're going to do, we know right, the distance between those two numbers and the distance between those two numbers. We know the distance here, so we're going to use this distance, right? We're going to use this distance to estimate this distance. Let's draw it graphically just to make sure we're all on the same page. So if we have, again, a graphical representation, we know, see, our dependent variable is going to be temp. So we have data here at 450, here at 500. We're looking for right here at 480. That's our unknown. Okay, so we know here at 450, this data point, that's 1.33607. And we know at 500, this data point, and that is up here, 1.48458. Right, all that we're going to do is get out my handy dandy ruler. We're going to draw a line between those 2 points. And, well, I can use my ruler again. Lost it. Come on, 90 degrees. Okay. And we're going to interpolate by taking 480 up to our line. And then taking that back across to our y-axis. I guess we'll call this our unknown specific volume, V. Okay, so this is all we're doing graphically. We're simply saying that we'll just draw a linear a line between these 2 points, 450 and 500, and then we're going to take 480 up to that line and use that to estimate what the specific volume is there. Now, in reality, the actual curve between 450 and 500 is not necessarily a line. In fact, it's not a line. It's some sort of curve, but as long as that distance is small and it's not really curved, linear interpolation doesn't give a whole bunch of error. So you can think of it, maybe the real data goes something like that. So we could have some error because our function is nonlinear. But in general, that's going to be fairly small, especially in certain parts, in certain regions, and especially if we have a lot of data. So if you tried to linearly interpolate using to 480 using the data from, say, 100 and 1000, you're going to get a different result than if you use 450 and 500, if we use data points that are closer together, because it's going to have more error like this. All right, so functionally, what do we do? Well, we have to look at these different dimensions. And we're going to do it assuming, here, I'll write just on the graph, right? We're going to kind of, this is how I think of it at least, and then we'll write the equation. So we'll call this, this distance 1, and that distance there, x. And then if we do the same thing over here, so if that dimension is 1, because this is a line, then this dimension here is also x, right? So we're going to be the same, because we're doing linear things. If we go, say, 30% of the way along here, or I guess, right, we're going from 450 to 500, so we're going 60% of the way. So this is, in this case, that's 60%. This would be, maybe this is an easier way to think about it, 100%. Then this is also 60% of the way between those two values. So that's functionally what we're going to do. The actual equation now is a little bit trickier, but how I typically do it is breaking it up. If you want to see the full equation, you can look in the thing from Felder. But I typically break it up like this and say, first determine how far or what this x value is. So we would go 450, or usually we do the larger numbers, it doesn't really matter. So it would be 480 minus 450 divided by 500 minus 450. So this gives us the percent that we are along the x-axis. And that's going to give us the percent that we are along the y-axis too. So if we want to know how far away we are from the bottom number, 1.33607, we're going to be 1.33607 plus 60% of the way to the top. So we're going to be, right, nu equals, let me move this over a little bit so I'm not crashing into things. So nu is going to be equal to 1.33607 plus, again, this is 60%. Now times the full 100%, so that's 1.48458. And then I'm running out of room. Apologize for that. Let me move this again. Minus 1.33607. So if we go and do this math, we find that nu is 1.42518, and then our units would be meters cubed per kilogram. So we can just look at this and see if we're right. I mean, the first check is, are we between these two numbers? Are we between 1.336 and 1.48? Yes, we are. And right, we looked at this graph, so we should be 60% of the way to 1.48. So we should be a little bit closer to 1.48 than we are to 1.33 or 1.34. And look, we're, again, just kind of ballparking it. We're about 0.06 from the top, and we're about 0.08 from the bottom. So yes, it looks like we are indeed closer to the top than the bottom. So those are just some common mistakes that you can make. Again, Felder has a fancy equation. It's essentially this equation, but all in, it's this equation, but they have it just all in variable form. But I think if you just look at it in your head, and I usually do this step by step in my calculator, I figure out, okay, what's the percentage here? What percent of the way am I along the x-axis? And that tells me the percent I am along the y-axis as well. And then I figure out, okay, then that times the full distance added to whichever side it is. So things can get a little bit more complicated. So I have a test yourself here at the bottom. The test yourself is find nu for nitrogen at 123 kilopascals and 295. So if you look at that, right, we're talking about now we're between 100 and 200. We're now between these four values. So now you're going to have to do two linear interpolations. And what I typically do would be something, I would make a little snippet of a table. I'll do it kind of over here in the side. So I would do 100 kPa, 200, so, and then, what is it, 280, yeah, 280 and 300. So then you have 280, 295, 300, and this is, I don't know what the numbers are, but this is known. So we know this one, this one, this one, and this one. We want this guy. So first you have to do an interpolation and find this one, then you can find this one, and then you can find the one in the center. Or you could do it differently. You could do first finding this point, then finding this point down here. So at 280 and 300 and 123 kilopascals, and then you could target the point in the center. So you could do either, this path. So do one interpolation to find 123, or you could do this path. Hopefully that makes sense. If you have to do one of these double interpolations, I always find it easier for myself to make a table like this, to make sure that you just keep track of everything and get everything straight. Hopefully that helps you as you go through the course. If you need to refer back to this video on linear interpolation, or just if you get used to using the equation from Felder, you're welcome to do that as well, but hopefully this helps you think about it. If you go and test yourself at home, the answer you should get for this challenge problem is down here.